My objective is to present several topics related to ASIC design methodology. I showed the front-end design mechanisms as well as the physical design methodology of an ASIC system on chip SoC. I also illustrate in this video the ASIC Universal Verification Methodology Environment, UVM. A quick synopsis about the ASIC design methodology, which consists of design entry, simulation, functional simulation, logic synthesis and test logic insertion, static timing analysis, simulation, gate level, formal verification, test structure verification, CMOS checks, floor planning, front-end processing, pre-layout, layout, final static timing analysis, post-layout, and ATPG and release to manufacturing. UVM is a methodology for building class-based verification environments in System Verilog, taking advantage of object-oriented programming techniques to help with code reuse. So reuse is right at the heart of the UVM environment. The building blocks of a UVM environment are objects, that is, instances of classes as opposed to modules, processes, and functions regarding the Verilog or VHDL. The significance of using objects is that they can be replaced at runtime, given a huge amount of flexibility when it comes to reusing verification components and tests without tampering with the original source code. You can take an existing item of verification intellectual property and replace subcomponents after the sequence of transactions it generates or extends its behavior without touching or copying the source code and without the original author of the VIP having needed to anticipate any changes. UVM environment recognizes three main types of user-defined object. The three main objects types are the component, the sequence item, the sequence where the corresponding classes are UVM underscore component, UVM underscore sequence underscore item, and UVM underscore sequence. Components are structural, that is, they are instantiated at the start of simulation, that is, during the build phase, whereas sequence items and sequences usually represent test stimulus and are dynamic, that is, they are instantiated on the fly at runtime. With System Verilog, I provide the mechanisms needed to create verification components for checking, coverage collection, and stimulus generation, and to modify the behavior of those components written in this specific test. UVM defines coding templates for the component, sequence item and sequence. Each of these coding templates is simple and regular, and the three kinds of template are mutually consistent. There are coding guidelines for the way the lines are ordered within each class and naming conventions for user-defined names, all of which make code look consistent. ASIC physical design methodology, the implementation for memory modules. The front-end mode consists of generating the SPICE models, which gives you the layout views and timing models. It also estimates power delay analytically. On the back-end mode, it generates the SPICE models with layout views and timing models to perform DRC and LVS. It can perform at each level of hierarchy or at the end of the hierarchy and simulates power delay, and it can also be back annotated. Physical design methodology for the ASIC 7nm technology in the artificial intelligence system. First, identify connections to be optimized after placement so that they will not influence the placement. These include the scan and clock connection to latches. Second, generate constraints for placement on the basis of a timing analysis done using idealized clock arrival times, add latches and estimates of wire load and RC delay before the physical design. These constraints include limits on the capacitance of selected nets and limits on the resistance of RC delay for selected connections. 3. Perform an initial placement to determine an improved basis on constraint generation, and optionally to fix the placement of large objects. 4th, generate new constraints for placement on the basis of a timing analysis done using wire load and RC delay values derived from the initial placement. 5. Perform the placement. 6. Optimize the clock trees and scan connections. 7. Make logic changes, including changes to circuit power levels to fix timing problems. Generate new timing constraints for wiring on the basis of a timing analysis done using the actual clock tree and wire load and RC delay values derived from the final placement. And finally, perform routing. Placement constraints. The area planner analyzes the distribution of the shapes and sizes of the library cells that take place in each macro cell and determines an optimal periodicity of circuit rows or columns and creates the placement structures based on each macro cell. This enables the placement functions to operate independently on different macro cells. The area estimation function described determines the appropriate width and height of each macro cell in the hierarchy. based on the wire demand in the X and Y directions, as well as for any child cells or other descendants down the hierarchy that have rigid shapes, in order to fit each macrocell and its siblings macrocells into the parent macrocell in an effective way. The floor planning tool will have a range of legal shapes for each of the sibling macrocells. Bit stacking methodology addresses the need for greater chip density and performance when bit stacking is applied to designs with a high data flow content, such as in this case, such as processors using large arithmetic logic units, registers, multiplexers, and shifters. The utilization of available gates or density is improved. The design of a bit stack uses general methodology. First, data flow logic is logically separated from control logic. Then each data flow bit position, typically spanning numerous data flow functions, is isolated and its circuits are placed along the same circuit row, minimizing the amount of wire required for the buses. Placement can be used at several points in the design process, and different algorithms are correct depending upon the state of the design. Placement is often run before the logic has been finalized to obtain an early indication of timing and wireability. At this point, the feedback may be used to influence logic changes. This may also be the time at which the locations of large objects are determined. The basic algorithms used in our placement programs are simulated annealing and quadratic placement with iterative improvements. Both simulated annealing and quadratic placement accept many controls. They include pre-placement, for planning, specification of circuits to be placed in adjacent locations, net capacitance, and source to sink resistance constraints, and weights for the various components of the scoring function, including net length, congestion, and population balancing. This segment describes some of the coding guidelines. The system-on-chip ASIC designed software models were written in VHDL. The basic software coding rule is that in order to obtain predictable results, code was kept simple. Therefore, the VHDL software models were generated and written to guarantee that the synthesis would produce the desired result. In many cases, synthesis would not lend itself well to doing a custom implementation of logic, since the exact structure of the logic is basically unknown until after synthesis. Even then, the structure is not always what may have been anticipated. An example, a regular structure such as an adder may be very easy to envision and to lay out, since there is a high degree of parallelism among all of the bits of the adder. So the same adder
when synthesized, may not have this level of parallelism. Each bit can be constructed differently. This places some limits on the ability to do custom layout of synthesized logic. My choice of synthesis and timing verification for this project was the sign compiler. So two separate mappings were done. One mapping was performed during test insertion. The software model operated on a single clock. The timing model reflected the correct timing and load values for the actual LSSD macro. After the final transformation was done, the clock splitter was pulled from the macro and the two LSSD clocks were reconnected between the splitter and the latches, therefore partitioning the design in two areas. Chrysalis Design Verifier is a formal verification tool that I used in order to logically compare different versions of the ASIC gate level netlist. I used this tool to verify that the different versions of the netlist did not change functionally during the design process, such as test insertion, placement, and route. This allowed me to proceed without having to resimulate at each step. Functional verification applied in this project. The primary objective of functional verification is to ensure that this ASIC design meets functional requirements. The functional verification process and methodology consists of gate level event simulation, gate level cycle simulation, gate level hardware acceleration, Boolean equivalency checking, and power estimation. The objective is to show the artificial intelligence system on chip VHDL implementation. The arithmetic logic unit is capable of calculating the results of a wide variety of basic arithmetic and logical computations. The arithmetic logic unit takes as input the data to be operated on call operands and a code from the control unit indicating which operation to perform. The output is the result of the computation. So the ALU, the arithmetic logic unit, will perform the following operations. The arithmetic operations, that is addition, subtraction, increment, decrement, transfer, logic operations such as AND, NOT, OR, NAND, NOR, exclusive OR, and also exclusive NOR. The objective is to show the implementation of a 32-bit arithmetic logic unit using the behavioral model style to describe how the operation of the arithmetic logic unit is being processed. It is accomplished by using the hardware description language, the VHDL. The behavioral style makes use of the process statement. The process statement
which is the main construct in behavioral model, allows using sequential statements to describe the behavior of the system over time. So a process is declared within an architecture as it is illustrated in this video and is a concurrent statement. The statement inside a process are executed sequentially. So the process reads and writes signals and values of the interface, which is input and output ports, to communicate with the rest of the architecture, like other concurrent statements. As I have illustrated and shown in this video of the arithmetic logic unit, I have used several constructs to model the VHDL process statement. Also, I have used the when statement. In the case statement, it executes many sequences of statements based on the value of a single expression. Also, the case statement evaluates the expression and comparison of the value of each of the choices, while the when clause statement corresponds to the matching choice, which will make the statement to be executed. The finite state machine, FSM, is a paradigm mathematical model whose output is dependent not only on the current state of the input, but also on past input and output values. The state machine generated in VHDL, as I have presented in this video, are clocked processes whose outputs are controlled by the value of a state signal. The state signal serves as an internal memory of what happened in the previous iteration. Using the state signal, the finite state machine, the case statement contains a when statement for each of the possible states, causing the program to take different paths for every state. The when statement can also contain code which should be executed while in that particular state. The state will then typically change when a predefined condition is met.
The control logic drives the FIFO flag. FIFO empty, that is flags, no data is present inside the FIFO RAM. In the FIFO full, no data can be written to the FIFO memory. And FIFO almost empty / full is also supported. So the FIFO almost empty flags is when the FIFO is used in order to buffer input data stream of a device where the input and output data throughput is the same, but the timing is different, such as in input as burst data, output as continuous data. The FIFO is used to buffer the minimum number of bursts data in order to guarantee continuous reading from the FIFO without interruption. So in this case, the FIFO read control logic block checks for almost empty flags going high and set FIFO read control signals to read continuously from FIFO. In the dual port RAM model segment of the FIFO, It writes counter to address the right side of the RAM. It reads the counter to address the right side of the RAM, and the control logic aiming to update the right counter at each write data into RAM, and the read counter every time a data is read or is read from RAM. The FIFO VHDL model has several settings and are configured to adjust the width and depth of the FIFO. The data width variables adjusts the size of the data in and data out buses so that one can write different sizes of bytes if needed, and the FIFO depth variable adjusts how big the internal memory of the FIFO is. In order to write data into the FIFO, first in, first out, first push the data onto the data in bus, and then strobe the write enable input high for 1 clock cycle. It will write whatever is on the data in into the FIFO's internal memory. Writing in bulk, the write enable signal is left high while changing the data on the data in bus each clock cycle. When the full flag goes high, this means the FIFO's memory is full and will not accept any more writes until data is read using the read enable input. If data is written while the full flag is high, it will be ignored. In the standard FIFO first in first out, when you write the first byte into the FIFO, nothing takes place on the data out bus until the read enable signal is pushed high for at least the clock cycle. Once the byte has been written into the FIFO, the empty flag will go low. To read the next byte from the FIFO, strobe the read enable signal high for 1 clock cycle, and the next byte of data will be available to read the next clock cycle. When the last byte of data is pushed onto the data out bus, the empty flag will go high.